We've been working on solving systems of nonlinear equations by graphing and or by substitution. Substitution being one of our algebraic methods of solving systems. So here we have a systems of equations that we'd like to solve algebraically. So as you're looking at a system algebraically, we're trying to see if we could do substitution typically, because elimination most cases would not work because typically you're using different types of functions. We can see we have a quadratic and a linear, so elimination would not work well with that. So if we're doing a substitution, we're trying to see, do we have an x equals or a y equals that we could use to help us start solving? And we can see that both functions are equal to y, so I could take what y is equal to 1 and substitute it into the other. So using substitution, we now have this quadratic equation that we need to solve. We know when we're solving quadratics, they have to equal 0. In order to do that, we need to move our pieces on the left to the right. So I could subtract the 6x, I could add the 3, therefore creating the 0 that I needed. So again, with our quadratics, we have a couple ways of solving. We could try factoring, we could do the quadratic formula, we could try completing the square. This would not be a good candidate for undoing or using square roots because we have the quadratic term and the linear term. By looking at our values here, I believe this is factorable because we could have -1 times -1 to give us a +1, and -1 plus -1 would give us the -2. So by writing it in factored form, that would help us solve it pretty quickly. Again, if you'd like to use one of the other methods of solving your quadratics, you're more than welcome to do so. Remember, the values that we have for x that we solve for should be the same no matter what method you're using. But when you're solving by factoring, the goal is to take each factor and set them equal to 0 and solve. So I've got x minus 1 equals 0 or x minus 1 equals 0. To undo each of those, we can add 1 to each side. So it looks like x equals 1. It's a repeated solution. So again, if you think about that graphically, that means the vertex is touching the x-axis at 1, 0. That's the repeated root or the double root, therefore showing up twice. Because it's a system, not only do we need to know what the value of x is, but we also need to know the value of y. So we substitute the values for x into the functions, and we solve for y. Again, which one you use is up to you. I used one of each to demonstrate the process. So again, we're working it out to find the value for y, and y equals 3. So it appears we have a repeated solution of 1, 3 for our system. The only way that we could double check and make sure this is valid is by taking the values 1 and 3 and substituting into the first equation and make sure it's balanced, and the same for the second. So again, by substituting in the first, we've got 3 is equal to 1 plus 4 minus 2. Well, that 1 and the 4 would be 5. 5 minus 2 is 3, so that works out okay. Substituting the second equation, 3 is equal to 6 minus 3. That's okay as well. Therefore, we have a solution to our system being at 1, 3. We always need to verify our solutions are valid by doing the check because we might have extraneous solutions depending on the functions that we're using, especially when it comes to absolute values, square root functions, or rational functions. So you always have to double check and make sure, is that solution valid?